Today we're going to talk about covalent bonds. Covalent bonding is a third type of bonding between two atoms. We've already talked about metallic bonding. We've talked about ionic bonding. Ionic bonding was a transfer of electrons between elements that were very different in electronegativity values, so that one atom really wanted to gain electrons and another atom wanted to lose electrons, and therefore they just simply transferred those electrons. In a covalent bond, we end up with a situation like this with these two fluorine atoms. If you look at the fact that both of these fluorine atoms have their 7 valence electrons, and our octet rule says that they're going to want to each gain an electron, so they both want to gain an electron. They're both. Then they don't have, neither one of them is going to willingly give up an electron to the other one. So the only option they've got in this situation where the electronegativity values, that tug of war on those electrons is the same, the only option they've got is to share. So what happens is they take that pair of electrons and they share it in an orbital. So when they share those two electrons in that orbital, it hooks those atoms together. It bonds those atoms together, and both attain a noble gas configuration, which you see right here. Now, covalent compounds are different from ionic compounds. Remember, ionic compounds have that crystal lattice structure of positive and negative alternating structure. When we're dealing with covalent compounds or molecular compounds, we have actual true molecules, individual molecules. So you would have, in the case of the fluorine, lots of little diatomic fluorines floating around that were individual molecules. Down here, it's just an example of some water molecules showing that they are discrete, meaning separate molecules. There's no lattice structure involved. Now we can use a Lewis dot structure to represent covalent compounds. If we've got two fluorines, and just for the sake of our example, I'll use a different color around this fluorine. We can see that those two fluorines join together. They share that pair of electrons, the red one from one fluorine, the blue one from the other. And we can rewrite that as kind of a modified structure. Different textbooks do it different ways, but I like the bonding pair of electrons, that shared pair of electrons, to be a dash in between those elements. So that's the way we're going to do it. Just remember, both of these structures are correct, and depending on the textbook you're going to find them in, it could be either one. Now, a double covalent bond is going to be made up of two shared pairs of electrons. So if you have something like oxygen, when oxygen hooks up, what's going to happen is that it's going to end up sharing two pairs of electrons. It's called a double covalent bond, or simply a double bond. I like it written again with dashes in the middle to represent those. A triple covalent bond, nitrogen is something that forms a triple covalent bond. A triple covalent bond simply has a situation where the elements are sharing 3 pairs of electrons. You end up with something like this. Again, I like it shown with the dashes in between. So there's the structures for a single, double, and triple bond. Now we can write Lewis structures of more complex molecules. There's a list of rules in your notes, but as with any rules, if you just simply read through them, they make absolutely no sense. They make more sense after you've seen a few worked out, and then when you have a glitch, you go back and look at them. So let's just go on to the next page, and let's just simply start writing Lewis dot structures for these molecules. The first thing that you want to do is to find the valence electrons for each of the elements involved, the total valence electrons. Carbon, if you look up carbon on the periodic table and look at the top of its structure, remember it has 4 valence electrons. Chlorine has 7 valence electrons, but notice there are 4 chlorines. So 7 times 4, we end up with 28 valence electrons for chlorine. That gives us a total of 32 valence electrons that we have to account for that are going to be involved in bonding for this carbon tetrachloride molecule. It's easier, since they are in pairs, to just talk about them as pairs of electrons. So I always divide those valence electrons by 2 to get the fact that there are 16 pairs. The next thing we want to do is to choose the central element, and the central element is always the one that there's only one of. Say that again. It's always the element that there's only one of. For instance, in this compound, there's 1 carbon. For chlorines, we're going to choose as the central element the one that's single carbon. Carbon's a diva anyway. I guarantee you, if carbon is in the compound somewhere, it's going to be in the center. And sometimes we end up with compounds that have like multiple elements that there's only one of. If carbon's in there, it's going to be the center. So carbon's in the center. The next thing we're going to do is to write the other element symmetrically around the carbon. Since there are 4 chlorines symmetrically around the carbon, they would look like this. And so there's the chlorines. Now we have 4 dashes showing right now, and each of those dashes represents a pair of electrons. So right now we've used up 4 pairs, and we still have more electrons to go. 12 more pairs to put around. Now this is where the octet rule comes in. The octet rule says that the elements, if they want any more electrons, that these elements will gain 8 total electrons, or 4 pairs around them. We always give the electrons to the outside element first, and then to the inside. It's, if you remember FOIL from math, first outside, inside last, we just need the OI part, the outside, inside. So we're going to give the rest of the pairs to chlorine first, and then if there are any left over, we'll give them to the central element carbon. So we've used up 4 in the middle, and now we're going to start counting out the others. So 4 used up, now 5, 6, 7. So we've got 7 electron pairs used up so far. Since the dash accounts for 2, that gives chlorine its 8 around. So we've used up 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The last thing that we want to do is to check and see if all of the elements have obeyed the octet rule. Now again, this is only going to be for the ones that want to get 8 electrons. Let's look back at our rule list, and you'll see a rule down here that says that groups 1A, 2A, and 3A elements won't get octets. We're not going to fill the octets for those elements. They're trying to lose electrons, not gain them. So we'll keep that in mind when we get to some of the later examples. So everything has 8 valence electrons. Carbon does, each of the chlorines, so that's a good structure. This is the Lewis dot structure for carbon tetrachloride. So let's go on to the next one, pH3. Once again, we're going to add up the valence electrons. If we look up phosphorus on the chart, phosphorus up at the top is 5A. That means it has 5 valence electrons. Each of the hydrogens has 1, but there are 3 of them in that hydrogen. or 3 hydrogens in that compound, so that's going to give us another 3 valence electrons. So we've got a total of 8 valence electrons, or remember, easier to talk about in terms of pairs. So 4 pairs of electrons that we want to account for. So anytime you want to work ahead as we work through these, please do so. I'm not going to stop and tell you to pause or anything like that, but you want to try to do these on your own once you get the pattern. Now, some of the later ones we're going to start having glitches, but let's look at this one. We've got phosphorus in the middle because it's the single element, and we're going to put the hydrogen symmetrically around it. There are 3 hydrogens, so we're going to put it around here in a triangular form. Now, keep in mind, we are not looking right now at molecular geometry. That's not for a couple of days away from this. We're just simply getting a basic structure. So we may find out once we get into molecular geometry that these look very differently than what we're portraying them on paper right now. So anyway, we've got 3 hydrogens around the phosphorus, and notice that we've used 3 dashes to do that, which means we've used up 3 pairs of electrons. We've only got 1 pair left to give to one of the atoms, and remember that the outside elements get them first, so hydrogen's got first dibs if it wants them. But remember where hydrogen is. Hydrogen is way over here in group 1A, and our rules say that if it's in groups 1A, 2, or 3A, they're trying to give electrons away. They don't want any more. They won't take any more. Hydrogen never gets extra electrons. So if hydrogen won't take that final pair of electrons, who are we going to give it to? We're going to give it to phosphorus. It doesn't really matter where you put the pair of electrons, but I'm going to show you in green how I do not want them. They can go in any space, open space, but do not put them like some kind of division line or something. Do not put them like that. Make sure they go in a space. So I'm going to get rid of those and make sure you're left behind with the structure like I want. So there's the structure for pH3. Now let's look at H2O. Again, find the valence electrons, 1 for each hydrogen, but there are 2 of them, so that's 2 valence electrons total. We look up oxygen. Oxygen's in group 6A, so it's going to have 6 valence electrons. So 8 valence electrons, or 4 pairs. The central atom's going to be oxygen, so put oxygen in the middle. The hydrogens are going to go on either side symmetrically. And if you know anything about water, you know that this is not the real molecular geometry of water, but this is how we're drawing the Lewis dot structures. So with those oxygens, with that oxygen with hydrogens on either side, we've used up 2 of our electron pairs. Remember that hydrogen, the outside gets first dibs, but does hydrogen want them? No, it does not. So the hydrogen will not take any extra electron pairs. The electron pairs are going to go on oxygen. So we can put a couple of electron pairs now to get our 4 electron pairs. Now we look at water, at this molecule, and decide if it has all of the valence electrons, if everything has an octet that wants an octet. Since hydrogen does not, we're good for hydrogen. Oxygen does, and it has its 8 valence electrons around it. Just keep in mind, I know this is the first time we've done this, just keep in mind that those dashes are actually representing 2 electrons each. So that's what's giving us our octet around oxygen. Okay, what about this next one? It's a negative you can't call it a negative compound, it's a polyatomic ion, but it's a negative species. How are we going to do this one? How is it going to be different? Well, chlorine has 7 valence electrons. Oxygen, remember, has 6, but there are 3 of them, so that's going to give us a total of 18. Now, second, if something has an extra electron, if it's negative, that means it has an extra electron in it, so we're going to add 1 more electron. There's 1 more electron present in this species. So anytime something's negative, you get more electrons. If it's positive, it means it's missing electrons. So in this case, we've got 18 and 7s, 25, plus the 1, we've got 26 valence electrons, which is 13 pairs. If you want to draw or pause this for a second and draw out that structure and see how you do on it, please do so. But chlorine is the individual element. It's going to be the central element. There are 3 oxygens that we're going to put symmetrically around it. And in doing so, we've used up 1, 2, 3 pairs of electrons. We still have 10 pairs to go. So we've used up 3. Outside gets them first, and oxygen is in 6A. It's not in groups 1, 2, or 3A. Oxygen wants electrons, so it's going to take them. So we've used up 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've used up 12, and all of the oxygens have their octet. So where's that last pair of electrons going to go? Exactly, on chlorine. The only thing that we do differently now, that everything has its octet, all of the elements that want 4 electrons have, or excuse me, 8 electrons have 8 electrons. Since it's negatively charged, we're going to do one extra thing. We're going to put it in brackets, and we're going to put the charge after it. That's how we do something that has a charge. Okay, NH4 plus is the next one. Nitrogen has 5 valence electrons. Each hydrogen has 1, but there are 4 of them, so that's a total of 4. Now remember, if it's positively charged, that means it must have a missing electron, which means we're going to take an electron away. So we've got 9 minus 1, we've got 8 valence electrons, or 4 pairs of electrons. So if we have nitrogen in the center, we have the 4 hydrogens around symmetrically. We've used up all 4 of our electron pairs, and the last thing we want to do is decide if everything is that wants an octet has one. Remember, hydrogen does not want an octet, so they're fine. Nitrogen does, and it has its octet. It has 4 pairs of electrons around it. So now remember what we do with something that's charged. We put it in brackets and put the charge after it. So now let's see what happens if we have another little glitch. Let's see what's going on here. We've got NaCN. Do the same thing we've done before. We've got 1 valence electron for sodium, 4 for carbon, and 5 for nitrogen. That gives us 10 valence electrons that we need to show doing something in this bonding process, or 5 pairs of electrons. But now we've got 3 different elements that we only have 1 of. We've got 1 sodium, 1 carbon, 1 nitrogen. What are we going to do with this? Okay, remember that if carbon is anywhere in the compound, it is going to be the diva. It is going to be in the center of everything. So we're going to put carbon in the center. We're going to put nitrogen on one side, sodium on the other. So we've used up 2 electron pairs in that process, and now we're going to put the other 3 on the outside first, outside first, then inside. Does sodium want any? And if you look back at the periodic chart and you see that sodium's in group 1A, you realize it does not want any more electrons. It's trying to give them away, in fact. So sodium does not get any more electrons. So does nitrogen want them? Yes, it does. It's in group 5A. We've already established in previous problems that nitrogen does want that octet. So we've used up 2 on the carbon, 3, 4, 5 for nitrogen. Now, at first glance, we might think, okay, everything's good. We gave nitrogen its octet. But recall that the last thing we want to do is to make sure everything has its octet that wants them. I always think of it as being, is everybody happy? And in this case, everybody's not happy. Carbon's not happy, and let me tell you, if carbon's not happy, nobody's happy. So what are we going to do? If you have a situation where you have used up your electron pairs and something still does not have an octet that wants an octet, you've got to think to yourself multiple bonds. You're going to end up with either a double or a triple bond, maybe more than one. So again, if you've used up electron pairs, but something still does not have an octet that wants them, multiple bonds. Now, there are only certain things that get multiple bonds. Let's look back at our rules. There's something we call CNOPs that we talk about, probably more often in AP, but CNOPs is a list, carbon, nitrogen, oxygen, phosphorus, and sulfur, a list of elements that form multiple bonds. And the only way, I repeat, the only way you can have a multiple bond between two elements is if they are both on this list. They both have to be part of CNOPs to form a multiple bond. So let's go back to our example. Are both carbon and nitrogen part of CNOPs? Yes, they're the first two letters. And so they can form multiple bonds. So what's going to happen? Carbon's going to look at nitrogen and go, you got all of your electrons and I'm missing two pairs, and that is just not going to happen. So I'm going to take one of your electron pairs and I'm going to force you to share it with me. And so it moves from being just around nitrogen to being between carbon and nitrogen. Now, is that good enough for carbon? No, it's not, because carbon still only has 3 pairs of electrons around it, and it will have 4. So what's it going to do? It's going to pull another pair of electrons over from nitrogen and share that as well. And so what we end up with here is a triple bond. We end up with Na attached to the carbon, which is a triple bond to the nitrogen with the electrons on the side. So that's going to be the structure of this particular molecule. So let's look at the next one, see what happens in the next one. CO2, carbon has 4 valence electrons, each oxygen has 6, but there are 2 of them, so that gives us 12 valence electrons total for oxygen. It gives us 16 valence electrons total for the compound, or 8 pairs. So we do what we've always done. We put carbon in the middle, we put oxygen on either side. We've used up 2 pairs of electrons between the oxygens and carbons, and we've still got 6 to go. Who gets it first? Yes, the outside, oxygen, outside then inside, OI. So oxygen's going to have, we've used up 2, 3, 4, 5, 6, 7, 8. And we've used up our 8 pairs of electrons, putting our valence electrons around the oxygens. Again, at first glance, we might think everything's good. But is it? No. We've got carbon with only 2 pairs of electrons around it, and we've already established that carbon's not going to let that happen. So, first thing we've got to do before we think about multiple bonds, because remember, if we run out of valence electron pairs before everything has an octet, we think multiple bonds. But can carbon and oxygen form multiple bonds? Remember that little anagram, CNOPs, for carbon, nitrogen, oxygen, phosphorus, sulfur. Both of them have to be part of CNOPs. And yes, it is. There's carbon, there's oxygen, so we can form multiple bonds. And carbon is going to simply take one of these pairs from oxygen and make it share. And since I'm sure that oxygen would think it was very unfair if it was made to share another pair, and nature does back this up, that symmetrical is better. We're going to share an electron pair from this other oxygen. So we end up then with, and by the way, I'm going to box this since we did some extra work on it. We're going to have carbon with double bonds around it. And since electrons do not like each other, they repel, we're going to put these other pairs of electrons as far away from those bonding pairs of electrons as we can. So kind of in a triangle shape, it's pretty much as far away from each other as you can get. So this is going to be the structure of carbon dioxide. Our last example on this page, we have NO3 with a negative charge. Nitrogen has got 5 valence electrons. Each oxygen has 6, so that's 18. What do we do if we have a negative charge again? We need an extra electron. So we've got 19 plus 5, we've got 24 valence electrons, or 12 pairs. So let's look at what NO3 does. We've got nitrogen in the middle, we've got oxygen around. So we've used up 3 of our pairs of electrons, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've used up our electrons. Have we used them up before we're full? Before everything has an octet? Yes, we have. Nitrogen is not happy. Nitrogen wants its octet as well. What's it going to do? It's going to force one of those oxygens to share. Now, it doesn't really matter which oxygen you choose. In AP, we find that situations like this end up with a condition called resonance, but we're really not going to get into that now. Just choose an oxygen and make it share. So I'm going to choose this bottom one, make it share. I'm going to take that electron pair and share it here with with the nitrogen. And we end up then, since it is negative, with it in brackets and a negative sign beside it. So that's the structure for NO3 minus. So those are some examples of some multiple bonds. The last thing that I want to talk about are exceptions to the rule. Situations where elements either don't have all of their octet or they have more. They have what we call an expanded octet. It's not anything you have to worry about figuring out or anything. If it tells you there are 5 elements around the central element, or 5 atoms around the central atom, that's what you're going to put. If it tells you 6, that's what you're going to put. So nothing we have to really figure out. We're going to follow the same rules. Now on BF3, boron has 3 valence electrons. Let me double check on that. Boron, if you look where boron is, yes, boron has 3 valence electrons. And each fluorine has 7, so that makes 21 total, or for the molecule, 24 valence electrons, or 12 pairs. And I'm going to do these pretty fast. We've talked about the rules. I just want to show you what these structures are going to look like when you get done. So we've got boron in the middle, we've got fluorine around the outside symmetrically. We've used up 3 pairs of electrons, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've run out of pairs of electrons. Is everybody happy? Now this time we think, oh my goodness, boron doesn't have enough, so it doesn't have its octet. We've got to form some multiple bonds. But then we look at our rule, and I have people, don't do this because it's wrong, but I have people all the time doing stuff like this, putting double bonds between boron and fluorine. But if you think about our little anagram to remind ourselves who can form double bonds, CNOPs, neither boron nor fluorine have any, they are part of CNOPs. Neither one of them can form double bonds with anything, so that's not going to happen. And then we think, oh, that's right, look where boron is. Boron's in group 3A. Do 3A elements want to have an octet? No. They're still trying to give away electrons. So boron is perfectly happy to be the way it is, and that's going to be the structure for BF3. PCl5, we have 5 for phosphorus. We have 7 for each chlorine, that's 35. Our 40 valence electrons total, 20 pairs. Nothing weird. It says to put 5 around it, do it. We will look at, oh, why this happens later, but for now, it says 5 things, it says 5 atoms around them, put them symmetrically around them, kind of a star shape for 5. We've used up 5 pairs of electrons, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We've used them up. Phosphorus has, it's extra full, but that's what it said to do, so we're going to let it go. It's an exception to the rule. It's an expanded octet. Expanded octet. SF6, 6 for sulfur, 7 for each fluorine, that's 42, so we've got 48 valence electrons total, 24 pairs. We've got a lot of electrons. I'll tell you, you will have dotted your paper like no other on this assignment, but we've got sulfur in the middle. It says to put 6 fluorines around it, so that's exactly what we're going to do. We've used up 6 pairs of electrons, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And everybody's happy, and sulfur's like stuffed. That's, again, it said to put 6, that's what we did. Okay, look at a couple of others. ICl2. Iodine has 7. Now this is going to be an instance where we have, those lone pairs happening. I'm just going to tell you up front, lone pairs going in on that central element, sometimes more than we expect. But we've got 7 iodines, 7 for iodine. We've got 7 for each chlorine, so that's 14, and it's negative, so we've got an extra electron. So we've got 21, 22 electrons, or 11 pairs. So we put iodine in the middle, chlorine on either side. We've used up 2 valence electrons, 3, 4, 5, 6, 7, 8. We put them on chlorine first. And now we still have pairs 9, 10, and 11. So we've got 3 more pairs of electrons to put someplace. Remember, once we get done with the outside elements, we're going to put them on the inside. It's a lot of electron pairs on the inside, but generally what I do, I will put like 2 pairs of electrons kind of offset on the top and another pair on the bottom. So we've got iodine now with 5 pairs of electrons. Again, it's stuffed, but that's what it has to have based on the number of valence electrons we have. It is negative, so don't forget to put it in brackets with a negative after it. Our last one, xenon has 8 valence electrons. Each fluorine has 7 for 28, and that gives us 36 valence electrons total, or 18 pairs of electrons. We put xenon in the middle. This is an example of one of our noble gases reacting with fluorine only. So xenon with 4 fluorines around it. We've used up 4 pairs of electrons to do that. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We've filled up the fluorines, and we've used 16 pairs. Now all we have left are 2 more pairs. Where are they going to go? On xenon. Usually it doesn't matter which you choose, but choose across from each other. Choose across from each other. So there's our 6 pairs of electrons around xenon. Expanded octet, but it's what it has to have in order to satisfy those valence electrons. So